All right, I'm going to start on magnetic, N-E-T-I fields. There's an L in there. And this will be the last chapter on electricity and magnetism. So this will be it. First of all, let's go with the magnetic field. Magnetic field. I'll just call it. I'm going to give you the symbol for magnetic field. It is the symbol we're going to use is B, and it's measured in Teslas. Aha! If you read anything in the paper, there's actually a charging station in Santee Cooper, not Santee Cooper, in the town of Santee, along I-95, and it is where the Tesla people that own their Tesla cars can charge them up quite quickly while they're getting a cup of coffee, and they have made it so along the I-95 corridor such that you can drive from New York to Miami charging your car back and forth. Isn't that cool? About 220-something miles in a Tesla. Pretty expensive cars, but anyway, it's an electric car. Oh well, it's named after Nikola Tesla. And so a Tesla, and capital T is the field, the unit for a magnetic field, and so named after Tesla. So I get an extra minute for that. Okay, all right. So here we go. Magnetic fields. So if you take the Earth, there it is, right there is the Earth, and this is the North Pole, magnetic North Pole. South Pole. You can get into discussions about how they reversed and reversal. And I actually took a class from a guy whose father figured out magnetic reversal. I'm sorry, not who figured it out. He was part of it. Opdyke, Neil Opdyke. So pretty neat to take a course. But he worked with Shackleton, Shackleton's son, who was an explorer in a great book if you want to read it called Shackleton. And he explored the South Pole. Ask me about it. I'll tell you a quick story about it. Anyway, I get another 30 seconds for that. Okay, so field lines come out of north and go into south, like that. And so they're coming out of north and are going into south. Didn't that sort of remind you of electric fields? And so, you could actually say that there'd be some coming, all the way around the earth. You know what I mean? I'm just doing dotted lines. So basically, let's just take it and imagine if we had a bar magnet stuck right through Earth. Not that it's like that, but let's look at a bar magnet. You're sort of familiar with this. It has a North Pole and a South Pole. So these field lines come out of north, and then they get turned around, and they want to go to where they're attracted to, and that's the South Pole. And so how do you find out the direction of a field? Well, you've actually done this for quite some time. Not a lot, but you've done it. If you take a compass and you hold a compass out and it lines itself up with one of these field lines right here, and it goes in the direction of that field. So if you want to know the direction of a field in a general area, then you put the compass in there and it'll line itself up. And if you put it out in Earth's magnetic field, it lines itself up with one of these lines, and that means it's always pointing towards the north in general. And but if you put it down close to a bar magnet, well, if you get really, really close to it, that bar magnet field becomes much stronger than Earth's field, so it will line itself up with that field. So magnetic fields. One, let's add this word in here too. Guess what? It's an electric field. It's a magnetic field. It's a gravitational field. They're all vectors, right? And so it has magnitude and direction. All right, keeping going. So you can, a current carrying wire, so here's a wire and it's carrying current, and I asked if I could carry it for it, but it said no, I'd rather carry it because I'm a conductor. And so if it has, let's see, a I for current going this way, then moving electrons create a magnetic field, a migration. Remember the electric field that is set up in the wire causes a force on the electrons, which will push them in a general direction. And so as these electrons move through a wire, they set up a magnetic field around them. And this we'll talk about a little bit more in class. This was actually by Oersted, I think it was. Yes. In a high school physics class, and back in the 1800s, it made the connection between magnetic fields and electric current. And I'll check on that name, but I'm pretty sure I've got it right. But so there is when wires have a current going through them, they also have I'm just going to write it here like this, a B field. Remember I said I was going to use that as abbreviation, B for magnetic. A B field, F-I-E-L-D, that's filed. What did I spell wrong there? Oh, wait, I see it. Okay. F-I-E-L, there's a D way over there. Okay. And so we're going to talk about this magnetic field that exists around it. And I'll tell you what, I'm not going to do it here on this. I'm going to do it in class. So if you want to add to your notes or leave some spaces, I'm going to use the right-hand rules for us to figure out the direction. Now here's the deal. We're going to have an equation. The magnetic field that exists around a current-carrying wire is mu O, and you can look that up. You might be familiar with, it's sort of like the E, the permittivity of a vacuum, and I'm just trying to let's see, and so remember EO and well, anyway, I'll explain it to you in class. Mu O I, where I is current. So in other words, the mu O is a constant based upon what it's in this case a vacuum, over 2 pi r. Now think about that 2 pi r. That ends up being the distance away from the wire, from the center of the wire. So we'll call that r. And so if you want to find the magnitude, so this gives you the magnitude. And think about it. Every time we've done a vector quantity, we get a formula that gives us the magnitude, and then we have to pretty much understand what's going on to get the direction. So for instance, if a car is being pushed to the right, we choose the right to be positive, then we assign it a positive magnitude. So anyway, we got the magnitude. There's the formula for the magnitude. Now all we have to do is get the direction. And the I'm going to abbreviate it, right-hand rule, or rules, right-hand rules, yeah, okay, is going to give us the direction. So stay tuned for those, and we'll get or don't stay tuned, just see me tomorrow, and we'll learn how to figure out direction. Okay. So big thing that you can get from that was the force on a current carrying wire has a magnetic field that exists around it, and we'll talk more about that tomorrow when I can show you and have you work with me on the right-hand rules. So what do we know? Magnetic fields go out of north poles into south poles. And that's sort of analogous, or not, I don't know if that's the right word, but similar to out of positive charges into negative charges. Same idea, coming in at right angles. Another one that gives you when a current carrying wire is, so here's I, is in the presence of a magnetic field. Now I'm going to do X's to show that the magnetic field in this case is going into the page. So this wire, see that wire right there? I'm going to actually make the wire yellow. So there's the wire. There it is right there. It's in this magnetic field, which I have designated as X's, meaning that it's going into the page. And so if this is, so think about it now. Got a current carrying wire. What does it have around it? Think about what I just said. It has a magnetic field. It's now in the presence of a magnetic field. So what happens when you bring two magnets close together? You can get a force acting on one, because remember, field forces can do action at a distance. So if you want to find the magnitude of the force on a current carrying wire, now you can write that down slowly. If you want to find the magnitude of the force on a current carrying wire, then you use the force is equal to the magnetic field that it's in, that's this X right here, times the current in the wire, times the length of the wire subjected to the magnetic field. And sometimes they'll put in sine theta if the wire happens to be coming in at an angle theta. Notice that it's perpendicular to it now. It's going across the page while the field is going into the page, which is a 90-degree angle. So that means this would go to 0. Okay? Or not 0, but 1. My fault. Okay, so there's two. Again, this has a right-hand rule, which is going to help us determine the direction of that force. This will give us the magnitude. Right-hand rule gives us the direction. All right, formula number 2. And then, let's see, force on a particle, and we'll wrap it up with that. Okay, remember I get a minute and a half more or so, all right? So let me see if I can wrap this up here with this. So let's imagine that you had a proton, and it was zipping through space, and here is that magnetic field again, and it's going into the page. Now, this is a proton. It could also be an electron, as long as it's a charged particle going along through space. Does that sort of sound like it's a current? Because here, I'm going to actually just use electrons. Sorry. So here's the electron going through space, and that's sort of like current. And think of it like that, So it has a magnetic field acting on it. So, or around it, it's So when it enters this magnetic field will be having a force exerted on it by this magnetic field. And so when it gets in there, what you'll end up seeing is that as it goes in, so this is the path that it's going to follow. Right when it enters, it starts. I'm put it to the bottom, so I got to do this. I'm going to make my magnetic field go this way. It actually starts getting pushed on, and it will actually curve. And so that's what we're going to talk about here. So that means that there's a force that pushed it toward, and it will be like a circular path. So it would be actually a centripetal force, if you want to call it that. That equation is F, the force on a charged particle that enters a magnetic field. So not until it entered here does this equation work, equals Q. You know what Q is? That's the charge in coulombs. It could be positive or negative, times the velocity of the particle, times B, times sine theta. So again, what is this giving you? The magnitude. Tomorrow, I'll give you a right-hand rule that will help you figure out the direction of the force acting on that particle. Okay? And with that, I'm going to stop right there. I think that's plenty for right now. So I think if you use the book and you look through it, you're going to be right up with what's going on. Now, on another note, if you happen to see this tonight, don't forget we have a test this week. I'm not going to really emphasize a lot of magnetism just yet because I wanted to get you settled in on that test. And I might even talk to you about adding this last chapter because it's actually not a very big chapter. We'll talk about it tomorrow. All right. Good night.